Our brain is truly marvelous. Billions of neurons communicating each fraction of a second. The question is, how could it evolve? Welcome to Psyched. The experience of our life is determined by our emotions. The happiness one experiences when being surrounded by loved ones, and the intense sadness we experience when losing some of those we love. Emotions like this enrich the perception of the world around us and make these perceptions more intense. Emotions are so important to us that they are an integral part in our behavior and identity. Bookstores are full with aisles of books about happiness, anger management, handling sadness, and so on. Emotions, to some extent, represent who we are, and thus they are crucial for the conscious experience of our surroundings. In other words, emotions are a fundamental element of our consciousness. Emotional processing in humans is so unique that it is hard for us to imagine emotional experiences of other animals. However, the way our emotions are processed share common brain networks with species in our ancestral line. Therefore, in this episode, we will take a deeper look into how emotions evolved. In the previous episode, we have seen how attention can amplify our senses and help us to select which information is relevant for survival. Emotions help to amplify this signal even further. Indeed, processing of emotions in the brain is linked to bodily reactions of sensory organs. For instance, fear is related to the widening of the eyes and increased speed of eye movements. As another example, disgust is related to shutting down our nose and mouth to avoid dangerous inhalations. But besides augmenting sensory information, emotions are also crucial for the way in which such information drives our behavior. As such, emotions help us to give a certain situation meaning. Is what I'm seeing, hearing, smelling, or feeling a positive thing, or is it a negative thing? Should I avoid it, or should I approach it? This is where emotions come in, since they convey a connotation to the attended stimulus. In its most basic form, emotions can be divided into an urge to approach or to avoid an interaction. For instance, a rival may induce both fearful and aggressive emotions, and which of those is expressed most strongly will determine an action. Whereas persistence of aggression can lead to an approaching behavior, in other words, trying to start a fight, fear will lead to avoiding actions, such as fleeing or freezing. But besides approach and avoidance, emotions can be split along another dimension, valence, which means how appetitive or aversive a stimulus is. This can result into emotions that humans would describe as positive or negative, such as the difference between happy and sad. Colloquially, emotionless actions are described to be cold-blooded. Based on this, one may expect that emotions only arose in warm-blooded creatures. Yet, this assumption is erroneous. Reptiles, birds, amphibians, and even fish have brain structures related to emotional processing and that are homologous to the brain structures we see in modern humans. As such, the evolution of emotions starts early in our evolutionary history. Avoidance of harmful stimuli is ingrained in the nervous system of all species since the early beginnings. As we have seen in the first episode, simple nerve nets have the ability to cause an organism to move away from a predator. A sense of touch activates a reflex arc that automatically triggers an organism to retract. This can be observed in species with even the most simple nervous systems, such as jellyfish. It would, however, be a stretch to label avoiding and retracting from dangers a fearful emotional response. But also, these same species show approaching behaviors towards nutrients. And also, we wouldn't attribute such behaviors to emotions like happiness or anticipation. Nevertheless, these approach and avoidance tendencies lay the groundwork for the development of emotions. The foundations of what we actually perceive as emotions most likely evolved in our fish-like ancestors, some 400 million years ago. Research in modern teleost fish, such as the sea bream, have shown distinct behaviors to appetitive versus aversive stimuli when these were presented in a high or low predictable situation. This suggests that these fish form some basic anticipation whether they like or dislike a certain stimulus. On top of that, cortisol levels are increased in sea bream when confronted with an aversive stimulus, suggesting some kind of stress response. Indeed, elevated cortisol levels and levels of distress are tightly linked to fight, flight, or freeze responses, and emotions such as fear and anger. In further support of these findings, it has been shown that threatening sounds can increase cortisol levels in fish, which in turn alters networks in the brainstem, increasing responses to sound. This would prepare an animal to be more responsive to similar threatening sounds in the near future. Cortisol, as well as other emotion-related hormones such as adrenaline, are regulated by the hypothalamo-pituitary-adrenal or HPA axis. As the name suggests, this brain network includes the hypothalamus and the pituitary gland. These two brain regions can be found at the ventral portion of the diencephalon, which is at the upper part of the brainstem. The hypothalamus is a complex brain region with dozens of subregions and nuclei, and they are involved in more than just fight or flight responses. It is thus impossible to say when the hypothalamus evolved, as it gradually became more complex over hundreds of millions of years. However, evidence suggests that basic structures that are homologous to what later would become the hypothalamus are already present in invertebrates. This suggests that the hypothalamus, an important foundational region for emotional processing, first developed before our ancestors split from modern invertebrates, more than 500 million years ago. Besides the hypothalamus, the telencephalon in fish has been associated with emotional processing. The telencephalon is the most upper part of the brainstem, which eventually would evolve into the limbic system and the neocortex in mammals. Particularly the limbic system is heavily associated with emotional processing. Although we do not use the term limbic system in fish, some elemental structures that over the next 400 million years would evolve into the limbic system, such as the dorsomedial and subpallium, can already be observed in the telencephalon of fish. Lesions to the telencephalon of teleost fish has resulted in altered fear responses, but also such lesions have led to the impairment of taste aversion, suggesting that not only fear, but also disgust is processed in the pallium and subpallium of fish. When we follow the evolutionary path to the point where our ancestors left the waters, we see emotional behaviors becoming more complex. Several modern amphibian species are territorial, and they mark their territories with olfactory cues to scare off potential intruders of the same species. If an intruder does decide to pay a visit, territorial amphibians can show aggressive behaviors. It has been suggested that these observations in modern amphibians would likely be very similar in the first land-living tetrapods. The increased reliance on smell and odorants in territorial disputes is also reflected in the brain. Amphibians do have a centralized hub in the telencephalon where connections of the olfactory bulb, hypothalamus, and pallium converge. This region is referred to as the amygdaloid complex, which is suggested to be the prototype region that would later become the amygdala. And the amygdala is one of the most crucial regions for emotional processing in humans. Besides basic emotions, such as fear and aggression, other emotions are usually not associated with our cold-blooded relatives. However, a large number of studies has provided evidence that some amphibians and many reptiles prefer enriched over barren environments. Enriched environments provide an animal with opportunities for activity, which allow for sensory or intellectual stimulation, which is not directly coupled to the immediate survival. In other words, enriched environments are preferred by animals that experience boredom. It is difficult to anthropomorphize boredom in reptiles, but it has been shown that various species of turtle, lizard, and snakes prefer to settle in enriched environments rather than empty environments when a choice is provided. So one may ask, what is the benefit of the evolution of boredom? Well, research suggests that sensory stimulation and playful behavior in response to boredom can provide an animal with a solution to potential future problems and challenges. So, playing and experimenting in a non-life-threatening situation can improve the chances of survival in future precarious situations. Behaviors that counteract boredom in enriched environments include playful behavior. Now, reptiles are not as fun-loving as your average puppy dog, but to a limited extent, playful behavior is demonstrably present in reptiles. Altogether, this suggests that emotions related to curiosity and happiness evolved before the first mammals appeared and gradually emerged between 400 and 250 million years ago. Unsurprisingly, within this time period, brain regions related to emotions developed accordingly. We observe an expansion of the dorsal pallium, and we see an increase in afferent connections to the thalamus. Within the non-synapsid evolutionary line, in other words, the ancestors of modern reptiles and birds, mainly the lateral dorsal pallium evolved, which is connected to sensory processing. However, in the synapsid evolutionary line, which contains all the ancestors of modern mammals, an additional expansion of the medial dorsal pallium is observed. It is this expansion which would, over evolutionary time, give rise to the hippocampus and the temporal lobe, which are important for long-term memory, as well as other neocortical regions. Although a network of regions including the amygdala, hippocampus, and hypothalamus is obviously present in reptiles, the term limbic system is often reserved for mammals. Indeed, emotional processing in these regions developed significantly over the last 100 million years. On top of that, during mammalian evolution, we observed the development of the cingulate, insular, and frontal cortex, which are directly or indirectly associated with the limbic system. For example, the cingulate cortex is often seen as an extended part of the limbic system, and it is crucially involved in regulating and recalling emotions. This expanding subcortical and cortical network have promoted social behavior, as well as multidimensionality of emotions, such as recognizing the difference between joy, excitement, gratitude, and happiness. Although all mammals have similar basic limbic structures, emotional processing differs quite significantly among species. One factor that seems to strongly affect emotional experience and understanding of emotions in others is whether a mammal is a part of a social group. Living in a social environment has led to the evolution of secondary emotions such as pride, jealousy, and trust. These emotions help to facilitate group structure, no matter whether this group is egalitarian or strongly hierarchical. An established group structure and harmony increase the chances of survival as a group, and this in turn increases the chances of survival of each single individual. Indeed, the expression of emotions is more strongly present in social mammals compared to solitary mammals. And the more complex the group dynamics are, the higher the understanding of emotional mechanisms needs to be within a group. It is therefore not unsurprising that we recognize emotions that are the most reminiscent of our human emotions in monkeys and apes, which have the most complex group structures of all mammals. Whether our earliest mammal-like ancestors already lived in groups is unknown. However, egg-laying marsupials, like echidnas and platypus, which are the best modern equivalents of our mammal ancestors, lived primarily solitary lives. This suggests that social life is more common in more modern species. Nevertheless, being part of a group is not the only factor that determines the quality of emotional processing. One other example is the rearing of young, which is far more common in mammals than it is in reptiles, although it is also quite common in birds. Taking care of offspring requires to determine needs, and this has contributed to the evolution of other secondary emotions such as empathy and nurturing behavior. Despite all the similarities and common brain structures related to emotion that we share with our ancestors, in one sense, human emotion is unique. Namely, we have developed the communication skills to accurately transmit our emotions. Language has given the human species a paramount advantage as a social species in survival, as it allows us to take better care of one another. It is language, in addition to our evolution of cognitive abilities, that makes us able to reflect, analyze, and even rationalize emotions. We are able to express what we feel with words and not just with bodily reactions. The interaction between language and emotion has become so strong in Homo sapiens that we are able to express deep emotions by words alone, in poems, stories, and song lyrics. The ability to express ourselves is not limited to emotions. An individual is a complex and non-linear summation of actions, memories, and experiences. Each of us is unique, and we often take pride in distinguishing ourselves from others. This requires us to recognize the identity of others and distinguish them from the identity of ourselves. It is our self-identity, in other words, who we are, that is the quintessence of what we would colloquially refer to as the mind or the soul. And it should be no surprise that this sense of self evolved. Therefore, in the next episode, we will discuss the evolution of identification of others and self-identity. We hope you enjoyed this episode, and we hope to see you the next time.